Hey, and welcome back. Let's do one more physics video. So for this one, we are looking at a very classic problem, which is talking about the center of mass of a system. The way that we typically see this is some sort of boat on a calm lake, something like that, and the objects inside the boat are moving around. So here we have Pete, who's 80 kilograms, and Dave, who's 120, are in a rowboat, that's 60, on a calm lake that is currently at rest. One of the pieces of information that immediately sticks out to me as I look at this is the fact that it's on a calm lake. And that means I'm not dealing with wind, I'm not dealing with a current, I'm not dealing with anything like that, which is going to help with this idea that there's no external forces. We'll talk more about that as we go. So it says Dave is currently at one end of the boat and Pete is at the other, and it gives us a distance. They're 2 meters apart. Before they take off, they decide that they should switch places so that Pete can row back to shore. So they've been sitting there, maybe they're having a snack, a break, maybe they're just looking at the scenery, and they decide, okay, it's time to go back to shore. It's now Pete's turn to row, so they're going to switch places. The question is, during this process, how far does the boat move? Well, the biggest conceptual here is the idea that there are no external forces. We know there's no external forces because this information came up here, meaning there's no air resistance, there's no wind, there's no friction, anything like that we're dealing with here. The other forces, if we think about, as they move places, the only forces that we're going to see is the force that Pete and Dave put on the boat themselves as they walk. But we know that due to Newton's third law, those are equal and opposite reactions. And so the boat's going to put them right back, making them an internal force, making them not really matter in this case. What that really means is we can say the entire force of the system then is equal to 0. And because of that, we know that this is from ACM, so the acceleration of the center of mass is equal to 0, which then really means that the acceleration of the center of mass equals 0, not just the whole force, which means the velocity of the center of mass stays what it was, which was also 0 because they're currently at rest. What that really means is the biggest idea in a problem like this is that the center of mass of the system, make that very clear, the center of mass of the system does not move. So you can say the delta x, center of mass of the system, is going to be equal to 0. So that is what we're looking at, and that's going to be the major concept that helps us solve this problem, is the change in the center of mass. When we think about the change in the center of mass, we think change is typically an initial and a final. So let's look at those two different diagrams. So I'm going to start, I'm going to just use the furthest edge of the boat to start as my 0. So here I have my boat. We're going to start, and I'm going to always have these names flip-flop. Pete is currently the one who's here, and he's 80 kilograms. We have Dave over here, who's going to be 120 kilograms. And then we're going to have the distance between them. We're going to call this distance L. Because the boat is perfectly uniform and didn't tell us otherwise, we're going to make the assumption that the boat center of mass is smack dab in the middle of the boat. If we look at this diagram, we can even think about the fact that we now have whoever this is way over here. If we look at this, we need to take into consideration his weight. Yes, this person is more massive, but he's at a larger distance, which makes me think that the center of mass of the whole system is probably going to be close to here. So I'm actually going to call that XCM, so we know which one we're talking about. In order to create an equation, let's look at the initial here. So we say the initial is the total mass, XCM initial, is equal to, well, each of the parts. So we're going to say the mass of Pete times Pete's initial location plus the mass of Dave times Dave's initial position plus the mass of the boat times the mass's initial position. And we're going to call that just the boat. I don't know what I said there. But the mass of the boat times the boat's initial position. And we're considering that to be the boat's center of mass because that's what's going to be moving. So now as we try and draw our after photo, the most important thing is we're not changing the location of our reference point because all of these distances are based off of this reference point, so it needs to stay exactly the same. As they move places, the center of mass of just Dave and Pete is going to change. So the center of mass of these two is going to change. It's always going to stay a little bit closer to Dave because he's a little bit more massive. So as he moves to the left, that means the center of mass of the two moves to the left. However, we know that the overall center of mass does not change. So in order to compensate that, that means the boat has to move to the right. So I did have to use a little bit of idea of just how the world works to help me draw the second diagram. Because of that, this is what my new diagram is going to look. I'm going to move the whole boat over to the right. Well, this distance here I'm going to define as d. This is the distance that the boat actually moved. We know that the boat center mass is still in the middle of the boat, so we're going to move that here, BCM. And if we were to draw this down, dot it down, we can see that there's this distance here, which is also going to be considered D because that's how far the boat moved. So it's going to be important as we start looking at our changes. On the other hand, we now have Dave over here. He's 120 kilograms. And we have Pete over here towards the front now, who's 80 kilograms. One of the important things to notice is that the center of mass of the system did not change. Obviously, this is not a perfect diagram, but we know that it would not have changed. So now we can go ahead and create a final equation. It's going to look very similar to the initial one, but now our distances are simply where did they end up. What's going to become really important is as we try to solve this, we want to talk about how things moved, where they went. What we're really looking for is the change in the center mass of the boat, because that actually represents the distance that the boat moved. So we're really looking at the changes here. I also knew I was looking at the changes because up here we knew that the change in the center mass of the system equals 0. So if we create that formula, we're going to say the total mass times the change in center of mass of the system is equal to, and I'm going to use some different colors here. Let's use pink to represent Pete. So it's obviously Pete's mass. And then to figure out how far did Pete go. Well, Pete started at 0, and he ended up here. If we try and figure out where he went, well, this distance, I'm going to dash it in black, was L. So Pete actually went the full L and then this extra distance. Well, this extra distance is how far the boat moved. So we can say that the change in distance for Pete is actually L plus D. So that's how far Pete moved. Nope, I was using pink. Changed my colors around. So now we're going to talk about Dave. Dave, on the other hand, started at L. He started over here at L, and he ended up here. Notice that isn't the full distance of L. It's really, he went backwards the L, and then he went forwards the D. So that's really his full distance there. And so we're trying to figure out his change in position. And so if we think about that as his final minus his initial, well, his final is just actually this distance D. His initial was actually just this distance L. So we're going to say for Dave, his change in position is actually just D minus L. So his final position here of D minus his initial position there of L. And then when you talk about the mass of the boat, well, we already defined the change in position of the mass in the boat to be this distance d. So we're going to substitute that in for its change in position. But now we go back to this very beginning idea. The change in the whole position is 0. So I can change that into 0 so the whole equation equal to 0. Now that we've done that, we're ready to solve. The variable we're solving for then is d. because that is actually defined as how far the boat moves. So notice we just figured out how far, what was the change in position of each of these people. And because the change in position of the boat or the whole system doesn't change, we can set this all equal to 0. The change has to kind of cancel each other out as a way of thinking of it. So now we're ready to just go ahead and do some algebra. We know that the really good skill here is move everything with the variable you want to the other side. I'm going to factor our common variables to the front. So I'm going to get L MP minus MD is equal, I'm actually going to factor out a negative D here. Notice that this quantity represents the total mass. If we solve for D then, what we're going to get is the mass of Dave minus the mass of Pete times L over that total mass. And so we take that all into consideration. When you plug all this into your calculator, you should get out approximately 0.31 meters. So when I looked at this problem, I debated, should I try to make it easier for you guys? Should we think about giving you the distance of the boat? Because then finding or how long the boat is, it might make finding this a little bit easier. You could actually put in a number to start. You would actually know that this BCM, say the boat was 3 meters long, would be 1.5. But really thinking about this idea that because there's no external forces, this change in the system has to be equal to 0. So therefore, all of the changes that happen have to cancel each other out. And so really looking at that and creating this final equation and thinking critically about, well, where did they start? Where did they go? And here's just another way of solving one of these very classic problems.